Hi, everybody. Thanks for joining us for the last week of Chandra Frontiers in Time Domain Science. Today we have neutron stars and magnetars, the first of 2 sessions today. The next one will start at 11:30. On Tuesday, we have 2 sessions on active galactic nuclei. That was a session at 9 a.m. Eastern Time and a session at 2 p.m. Eastern Time. And then on Friday, we have a full day, the last day of our workshop, 2 discussions on multi-messenger astronomy. One of them is a panel discussion, and then we have a closing event, which will include a summary talk from John Miller of University of Michigan. Oops, there we go. Today's session that I'm going to introduce to you now is Neutron Stars in Magnetar 1. We have a slate of speakers today, a couple of lightning talks, and 2 invited speakers. Our first invited speaker, if you can start sharing your slides, is Nathalie Degenaar from University of Amsterdam and Anton Pannekoek Institute for Astronomy, who will talk to us about accretion and outflows. Sorry. Accretion and outflows in neutron star low mass binaries.
Yes, does that look good?
That looks good. All
right, thanks. So thank you. I am Nathalie Degenaar of the University of Amsterdam, Anton Pannekoek Institute for Astronomy. I'm a faculty there, and it's my pleasure to share with you today some Chandra highlights on time domain studies of neutron star X-ray binaries. Now, of course, last week we had an entire session already on X-ray binaries in this virtual online conference, and only rightfully so. If you go on RDS and you do a simple search on abstracts and you look, for example, on Chandra and then Chandra and X-ray binaries, you'll find that you can estimate that about 20% of Chandra science is on X-ray binaries. So that's quite a significant fraction. And you'll also find that doing studies of X-ray binaries really requires time domain studies, which is what we're talking about in this Chandra series, of course. And the reason for this is that X-ray binaries can be detected over a very wide range of X-ray luminosities, from about 10 to the 30 to 10 to the 39 ergs per second, which corresponds to about 10 times the Eddington limit for these X-ray binaries, down to a tiny fraction of it. Moreover, X-ray binaries vary on very wide timescales, ranging all the way from milliseconds to decades. So there goes your time domain studies. Now, it's not very easy to give a review of X-ray binaries, simply because there's a wide range of topics that we do in this research field, and that Chandra has made major contributions to. So to reflect this, I've just made a simple word cloud, picking words from abstracts from NASA RDS, and you can see that there's a wide variety of topics, all the way from studying variability, timing, to studying spectroscopy, of course, studying neutron stars, black holes, ULXs, winds, and whatnot. Now, it is important to emphasize that Chandra has made major contributions to many subtopics in X-ray binary research. And the sessions that we had last week on Tuesday and Thursday are a very nice reflection of that. All right, so what to choose then for a review talk? Well, first of all, I'll focus on neutron stars, because that was the request. So I'll talk about neutron star X-ray binaries, and I focus particularly on the ones that have low mass companions, so low mass X-ray binaries. The companion then has a mass less than about 1 solar mass. And the neutron stars in these systems have weak magnetic fields of typically up to 10 to the 9 Gauss or so. Now, from all the possible topics that you can pick for X-ray binaries, I've chosen 2, because I think that Chandra has made some quite significant contributions, in particular there, and we might further develop in the next couple of years. The first of these is disk winds. Of course, we have seen an excellent review talk last week by Joey Nielsen about accretion disk winds, focusing on black hole systems. I would like to share with you some cool results also on neutron star systems, in particular showing that in neutron star X-ray binaries we detect disk winds over a very wide range in mass accretion rates. And then the second topic that I would like to share with you is to show that X-ray binaries are extremely good objects to also study neutron star physics. And the reason that I chose this topic is because it hasn't been covered yet so much in this conference, and also, of course, it connects nicely to the sessions that we are now entering on neutron stars and magnetars. Now, as we go, I'll focus, the topics that I focus on are particularly making use of the strengths of Chandra, of the gratings, high spatial resolution, and the sensitivity at soft X-rays. So to start off with setting the context for the first topic, for these winds. Now, the reason why this is a very important topic is that accretion in all kinds of accreting systems is universally linked with outflows. And these come basically in two forms, either disk winds, which you see in the top artist impression over here, or jets, which you see in the bottom, which are more collimated. These jets we typically detect in the radio band, and these winds we typically detect as absorption features at different wavelengths. Now, these outflows have a very important impact on X-ray binaries. And the first point of impact is that they can give significant mass loss of the binary. And we think that this can influence the accretion flow significantly. For instance, we think that maybe by losing mass through disk winds, these winds may actually destabilize the accretion flow, perhaps causing so-called state transitions that we see in X-ray binaries. And if the mass transfer in X-ray binaries is highly non-conservative, so if they lose a lot of mass through outflows, then this might have a significant influence on how the binary evolves. For example, accelerating the orbital decay of the two binary components, and thereby making the time until they will eventually collide shorter. So this is the first point of impact. The second point of impact, quite literally, is that these outflows might have significant kinetic power, and thereby, by flowing away from the X-ray binary, might influence their environment. So, for example, the interstellar medium that surrounds these X-ray binaries. Now, that they might have a significant impact there is nicely illustrated by this beautiful radio image, which was published by Elena Gallo already 15 years ago. And it shows a radio image of black hole X-ray binary Cygnus 61, which is the tiny radio blob that you see already in the bottom. What you see is that there's this large extended bow-shock structure around the X-ray binary. And we think that this is where the very strong radio jet of this source is slamming into the ISM. Now, through these interactions, X-ray binaries might actually heat the ISM, create turbulence, thread it with magnetic fields and whatnot. And there has been some speculation that perhaps by these interactions with outflows from X-ray binaries and the ISM, they might actually play a role in galactic feedback. So, for example, stimulating star formation and whatnot. Now, the limited knowledge that we currently have, we think that mass loss is most significant through disk winds. So we think that disk winds are probably more mass loaded than jets. And these disk winds is what I will focus on today. So I will focus on the neutron star systems. For the black hole systems, you can look back to Joey Nielsen's talk of last week. Now, we think that on the other hand, that probably jets have more kinetic power than disk winds. But I will not focus on jets today because we had some excellent talks last week, for example, by Aaron Shaw and Alex Tatarenko, which were also clearly emphasizing the time domain aspect. That also involves Chandra, and also later in this session we'll have a neutron star jet talk also by Teresa. All right, so talking about time domain science, what we will see is that there is a very strong connection between the outflow, so the jets and the winds of X-ray binaries, and the accretion inflow. So it matters a lot how much matter is flowing inwards, and that determines how much matter is flowing out. Now, this is where the interesting aspect comes in. As I mentioned, X-ray binaries can be observed over a large range of mass accretion rates, and therefore we also see large differences in the properties of these outflows. So this is something that I will highlight today. Now, one way to show this is by showing you a typical light curve of a transient X-ray binaries. Many of the X-ray binaries that we see are actually not persistently accreting, but they go through these phases of accretion outbursts that typically last a couple of weeks or maybe a couple of months. And during such outbursts, we see the accretion luminosity or the accretion rate increase by orders of magnitude, as you see in this example over here. Now, with these large changes in accretion rate, we also see large changes in the accretion morphology and hence in the properties of the outflows. So just to give you a very simple, simplified sketch, what we think that what we typically see at the highest accretion rates in X-ray binaries, so around the Eddington limit or a few tenths of % of it, we typically see in our X-ray spectra a very bright accretion disk. It's very prominent. And we can also typically detect winds from X-ray binaries. Now, if you drop in accretion rates to a few % of Eddington, maybe a few tenths of %, so you have lower accretion rate. What we then see on our X-ray spectra is that disk is fainter, and instead we see more prominent emission from what we call hot electron corona. Now, there's typically in these at these lower accretion rates that we often don't see the disk winds anymore, and instead we start to see strong radio jets. And then if we drop even further, so down to less than say a % of Eddington or so, it becomes a bit more difficult to study X-ray binaries simply because they become really faint, as you can see in the slide curve over here. One of the predictions of standard accretion theory is that the disk significantly starts to truncate away from the black hole or the neutron star, so it shouldn't be able to reach close to the compact object anymore. It's quite likely that there are also outflows. We have some cases where we see clearly radio jets down to very low accretion rates, primarily in black hole systems, and maybe there are also unbound flows in the form of wind. But there's more question marks here. And then at the very lowest accretion of very lowest X-ray luminosities that we see in X-ray binaries, possibly accretion is completely stopping, or at least the accretion rate is incredibly small. And we think that the accretion disk is truncated very, very far away from the black hole and the neutron star. And we don't really know if there's much outflows going on right here. All right, so I'll be focusing on disk winds. So how do we observe disk winds? Of course, we had a nice talk by Joey Nielsen already last week, so I'll be relatively brief. Disk winds we typically don't observe by direct emission. Instead, what we do, how we detect their presence is that we're looking at some kind of primary X-ray source, and we're basically looking through the wind at that source, and the wind is absorbing the primary emission. So what you see here is a beautiful example from Chandra grading spectra published by John Miller in 2006 in Nature on a black hole X-ray binary. And what you see here is this beautiful collection of narrow absorption lines. And in blue, you see the data, and in red, you see the rest wavelengths of these elements. So you see that there's a blue shift between the data and the rest wavelengths. And if you have such a high quality and high resolution spectrum, there's a lot of information that you can get from this. You can measure the line species, the line shift, the line width, the line depth, and whatnot. And all this gives you physical information about the plasma that is doing the absorbing. So you can, for instance, infer the velocity of the plasma. Is it inflowing? Is it outflowing? Its ionization state, its density perhaps, and also the location of where it's outflowing. So basically how far it is from your primary source. Now, there's many questions that we still have about these disk winds. For instance, how they are actually launched. So how do we produce X-ray disk winds? What is their actual mass content, and is the mass that is being carried away by this disk wind, is it actually lost from the system, or does it somehow fall back? What the role these disk winds have in the overall accretion process, and also what their connection is with jets. So on this last topic, the connection with jets, there's something interesting going on here. This research started about more than 10 years ago by John Miller et al. He was doing Chandra studies of disk winds, and he had this beautiful example that you see over here, where you can see how the wind is evolving with changing accretion state. Now you see here beautiful absorption lines in the bottom three spectra. So these are clearly the hallmarks of a disk wind, but you can see in the top spectrum that when a strong radio jet is detected from this black hole X-ray binary, suddenly these absorption lines disappear. So there's some suggestion that the winds and the jets are not detected at the same time. This was also beautifully shown by Joey Nielsen and Julia Lee in the Nature publication in 2009, where they showed that there is really an anti-correlation between the appearance of the wind and the jet in one other famous black hole, GRS 1915. And then a couple of years later, Gabriele Ponti did a nice study of an entire sample of black holes, showing that typically when these black holes show strong radio jets, there's no X-ray wind seen. So this led to the observational paradigm that X-ray winds and radio jets do not occur simultaneously, and possibly this has to do with some kind of thermal instabilities in the plasma. Now, the last few years, there have been a little bit of, we've been moving away from this a little bit. There's more and more evidence that there are actually sometimes occasions where we can observe disk winds and jets at the same time in X-ray binaries. And one example, for instance, that I won't talk too much about today is that in the last couple of years, Theo Munoz-Darius and his group has been detecting a lot of optical winds from X-ray binaries, from primarily black hole X-ray binaries, during states when they also show bright radio jets. Now, we don't know yet how these optical winds are related to X-ray disk winds, whether they're part of the same phenomena or whether they're completely different. So I'll focus today only on the X-ray winds and not go into the optical winds too much. All right, so we have this observational paradigm of winds and jets not coinciding, but I'll give you a few examples of neutron stars over the entire range of mass accretion rates where it appears that we actually always see these winds, and also in connection with radio jets. So the first one, I'll go from high to low accretion rates. The first example that I want to show is GX 13+1. This is a very bright neutron star system, and it persistently accretes at about 50 to 70% of the Nx limit. And we happen to know that it has an orbital period of about 25 days. Now, because this is such a bright neutron star binary and it is persistent, it's been known for decades, and it has also been studied for a long time already. So it was also part of early radio jet studies, and it was known from very early on that the radio emission in this system is varying. Sometimes it's even disappearing. And later studies showed that these variations of the radio emission actually correlates to X-ray spectral states. And one way to see this is this nice plot from Johan Homan et al. 2016, which shows a color diagram, which is sort of which is one particular way in which you can show different accretion states in an X-ray binary. The details of this are not super important, but to take what is important to take away is that there are certain places in this color diagram where you do see strong radio jets, which are the orange points on the top. And then there's other parts of the diagram where you see a very weak or no radio jet at all, which are at the bottom part. Now, disk wind studies came along a little bit later after the launch of Chandra, but here's nice, some nice results on this particular source. These are again the same color diagrams, but here the red points indicate Chandra observations where you clearly detect a radio wind. Where you clearly detect an X-ray disk wind. So what you can see is that there is very clear X-ray disk wind detections in the same part of the diagram where there's also radio jet detections. And the outflow velocities that are reported for the disk wind of this particular system are about 400 to 800 kilometers per second, which is quite typical for X-ray binaries. Usually we see outflows in these systems of about 300, maybe up to 1,000 or 3,000 kilometers per second or so. So this just shows that at a very high accretion rate, at least just below Eddington, neutron stars can show both radio jets and neutron stars, radio jets and disk winds, sorry. Now, if we make one step down on the accretion ladder to intermediate rates where we typically see radio jets, I have another nice example for you. This is a neutron star called IGRJ 1759. This happens to be a so-called AMXP, which is an accreting millisecond X-ray pulsar. And what this only means is that either the accretion rate is low enough or the magnetic field of this neutron star is strong enough, or both, that the neutron star is able to channel some of the accretion material from the accretion disk to its magnetic poles. Magnetic poles will therefore heat up, and as the neutron star rotates, you will then see sort of a lighthouse effect, which we call an X-ray pulsar. This is nice because it allows you to measure the spin period of the neutron star. In this case, it happens to be a little over 500 Hertz. Now, this neutron star accretes at low rate, only about 1% Eddington, and we know that its orbital period is almost 9 hours. This is a transient system, and it had an outburst in 2008, and Tom Russell did a very nice radio study of this, this neutron star. And what you see here is its radioluminosity versus its X-ray luminosity in this diagram, compared to a whole bunch of other neutron star and black hole systems. In this diagram, all the filled black dots are the black hole systems, and the open filled dots and the colors are all neutron star systems. Now, at the time when this study was published, the distance to the source was not known yet. Therefore, there's different symbols plotted. But recently, Lucien Kuiper actually discovered thermonuclear bears from this system, which allow for a distance estimate and show that it's around 8 kiloparsec. So the relevant points for this source are the orange one that are up here. Now, what you can see is that it's extremely bright compared to other neutron stars. It's all the way around along the black hole populations, and there's no other neutron star that is so extremely bright. So that's already interesting. Now, what's interesting as well is that Mike Nowak did an independent study with Chandra, with the gratings, and here's a plot from his work showing the region around the silicon K edge, and you see this nice absorption features over here. And this can be interpreted as a disk winds being present in this system with quite a high outflow velocity of about 2,400 kilometers per second or so. And these Chandra observations that showed these features were taken only a few days after one of the bright radio detections of this neutron star. So it seems that for some reason, this neutron star, which is accreting at intermediate rates, quite low, is able to sustain both a very bright radio jet and a relatively fast disk wind. Why it is able to do so is not really clear. It's not a particularly unusual system in terms of orbital period or spin period or whatnot. So it's not really clear why it is doing this and whether it should be common or not. All right, going down even lower to the lowest accretion regime, around below 1% Eddington or so. It gets tougher and tougher to study these systems because they become so faint. I want to show you one example, which is a neutron star called IGRJ 1706. This is again an accreting millisecond pulsar, and this one happens to be spinning at little over 100 Hertz or so. Has a very low accretion rate, only about 0.1% of Eddington, and we know that its orbital period is very short, only about 38 minutes or so. Now, we try to look for a radio jet from this source because we normally expect these in this accretion regime, but we didn't detect it, although it was not very constraining. With this source, we're, because of the X-ray luminosity so low, we're really pushing current radio capabilities. So the fact that we don't see a radio jet doesn't mean it's not there. Now, talking about pushing capabilities, we try to do the same thing with Chandra to look for a disk wind in this system. And here you see some plots from that. What you see over the left is the data from the true the grating arms of Chandra. And what you can see is that the data is very noisy, error bars are large, but there are some hints of narrow features in these spectra. And what you see over at the right is line search that Ciro Pinto performed with the same algorithm that he also uses to find winds in ULXs, which we heard from Felix first last week as well. And what you can see from this plot is that there are a few lines poking up both in emission and in absorption that are slightly over 3 sigma significant perhaps. So we also tried to model this spectrum just to get an idea with some physical models with Pion and BAPEC, and that suggests that perhaps there could be a disk wind in this system as well, with an outflow velocity of quite high, of about 2,000 to 3,500 kilometers per second. Now, I'm not pushing on this result particularly hard because clearly the data is very noisy. We're really pushing the Chandra capabilities, but it is interesting that there are some hints of outflows. We tried to do the same later on with XMM Neutron, with RGS, and there we got the same results. So we also saw these narrow features suggesting the same results, also some outflow present. Now, an alternative argument that seems to suggest that there is some mass being lost from this binary, perhaps in a wind, is from a study by Juan Hernandez Santisteban, who looked instead at the UV optical and infrared spectral energy distribution of this source, which you see plotted over here on the right. So on the left part of the plot, you see all the X-ray stuff, and then on the right part, you see all the observations from this source at UV optical and infrared wavelengths.
3 minutes.
We modeled this multi-wavelength spectrum, and he found that there is significance of he found that it can be perfectly described by a standard accretion disk. And when you do such modeling, you can actually infer how much mass needs to be transferred into the disk in order to explain your observations. And by comparing this with the results from the X-rays, which should be some kind of trace of how much matter is actually accreting onto the neutron star, he suggested that more than 90% of the mass that is entering the disk, so what we trace with optical, UV, infrared, is actually not being accreted by the neutron star. So it suggests that there might indeed be some strong outflow present. This might not be uncommon. There's actually indirect evidence for strong mass loss also in other accreting millisecond pulsars. And this indirect evidence comes mainly from their very rapid orbital decays, which suggests that there is some highly non-conservative mass transfer going on. I'm just listing two examples of where these things are studied. All right, so then we drop from low accretion rates to quiescence, where I go to the second topic, neutron star physics. But before I do so, I just briefly wanted to mention that there is this very peculiar class of neutron stars that somehow seem to transition between a state in which they are not accreting, that actually can be observed as radio pulsars, to some kind of low mass X-ray binary-like state in which perhaps they might be accreting or not. And we call these systems transitional millisecond pulsars. They're super interesting because they give us links between different populations of neutron stars. And I will not go into them because last week there was an excellent talk by Arash and Baramian on these type of systems. I just wanted to mention in the context of this particular talk that these transitional millisecond pulsars, so if they are accreting, they're accreting at very low rates, and they also have strong radio emission and also evidence for outflows in the UV. So then again, neutron stars are producing outflows. All right, quiescence then. If a neutron star is not accreting, then we can actually do something cool. We can actually look at the neutron star itself and detect thermal radiation from its surface. Now, what is so nice about a neutron star and X-ray binaries is normally when neutron stars are formed, they're very hot and then they cool down over time. When neutron stars are in X-ray binaries, they get reheated during accretion episodes. When the neutron star is accreting, the crust is, there's all kind of material falling onto it, the crust is being compressed, and all kind of nuclear reactions generate heat. Now, when accretion switches off, the heat generation in the crust stops, and then we can actually observe the temperature of the neutron star cool down. And one example of this is shown in this plot over here. So you see on a time scale of many years, you can see the temperature slowly going down. And this is how this accretion heated crust is cooling down. Now, when you have these kind of observations, you can actually compare them with theoretical simulations where you heat a neutron star up and you let it cool down depending on all kinds of interior properties of the neutron star, for example, how its superfluidity is, how the cross structure is, what the density of the core is and whatnot. And by changing your models and trying to match it with the data, you can infer all these interesting physics about your neutron star from these kind of observations. I just wanted to note that I'm talking about neutron stars in low mass X-ray binaries, so with low magnetic fields, but similar studies have also been performed for neutron stars with strong magnetic fields. And in the next session, there's a nice talk by Alicia Rucco Escorial about this, which I can highly recommend. Okay, just briefly, some things that we've learned from these cross-cooling studies are quite surprising. The first of them is that I wanted to highlight is that we found some kind of extra heating mechanism in the crust of neutron stars that we don't understand at all yet. And Chandra had a major contribution in finding this out because the first source for which we found it out was in a globular cluster, Terzon 5, which you see over here. So we needed Chandra's spatial resolution to study this object. So what you see here is this neutron star is also cooling down after an accretion outburst, but what you see in the dotted line in this diagram is what we were actually expecting for the temperature evolution of this neutron star based on our current knowledge of nuclear heating, so the nuclear reactions that should be occurring during accretion. So this neutron star was much hotter. We needed to put in all kinds of extra heat to explain our observations. And we've later inferred similar shallow heating sources for other neutron stars, but we don't actually know where the shallow heat should be coming from. So we basically don't have a clue what is generating this heat. All right, then one other brief result concerning neutron star physics that I wanted to show is when you have this crust of a neutron star and it's cooling down, of course, the outer layers are closest to the surface, so their heat will be diffused to the surface quicker than layers that are deeper. So the longer in time you look after an outburst, the deeper and deeper crustal layers you're basically probing with your observations. Now, Astronomy published a work this year actually where two sources that she'd been following for over a decade suddenly showed an increase in temperature very late on at around the same time. This is not really what you expect. You just expect the neutron star crust to cool down and keep cooling down, but she observed this temperature increase. It's very hard to explain this with some kind of unseen accretion event, especially since it occurs in both neutron stars at the same time. So we've been speculating whether this perhaps has to do with some kind of weird layer in the neutron star crust is about at the depth of where you might expect nuclear pasta to occur. But we were not able to make it work yet in our models. So maybe this is just exposing some kind of new neutron star physics that we don't understand yet. All right. I will skip over this because I don't know my time, and I will jump to the summary. So it's important to remind that Chandra is extremely important for studying many different aspects of neutron star X-ray binaries, and I've discussed only two different topics. The first of two is that disk winds occur in neutron star X-ray binaries apparently at all accretion rates. So we have examples of neutron stars accreting at different rates that all show disk winds. Whether this means that disk winds are present all the time, of course, we don't know, and we don't know yet what actually determines whether these disk winds are there or not. And the reason that this is such an important topic is because understanding how disk winds work is important for accretion physics and also for binary evolution. And the two major questions that we still have about this is how disk winds are being launched and how much mass they actually contain, and that if they can be a significant source of mass loss for an X-ray binary. Now, the two things that we can still do with Chandra to go forward on this is, first of all, that there should be proper monitoring along an outburst, ideally, to see how the wind evolves. There's has been some fantastic efforts to try and do this for black holes already. So to actually see how a wind accelerates when it starts and whatnot. But I would argue that we also need to do this for neutron stars. So one of the reasons is that maybe there are reasons that neutron stars are better able to launch disk winds. We are probing different parameter regimes if we look at neutron star X-ray binaries and compare them to black holes. For example, neutron stars spin slower, typically their accretion disks are smaller, and maybe the neutron star surface or its magnetic field can also play some role in how disk winds are being observed. Of course, doing these wind studies is quite a burden on Chandra because it requires quite long exposures typically, and ideally you would need several TO observations along the course of an outburst with a response time of say a couple of days, maybe a week or so, because this is the time scale in which large changes can occur that you would want to trace. Now, the second part where we can still make steps forward in studying disk winds is to make a connection with the winds that are seen serendipitously at UV, optical, and infrared wavelengths. As I mentioned briefly, there are some detections of winds at these wavelengths, but we don't know yet whether they are connected with the X-rays or not. In order to find out, we would ideally need to do multi-wavelength TO coordination with, for example, HST and VLT, and so on. And the reason why I think this is important, that if you Maybe if we're looking at X-rays, we're only taking a tiny snapshot of the disk winds. So if you want to understand completely how they are being launched, how much mass they contain, you should be looking across the electromagnetic spectrum. Of course, this is another challenge to schedule. Then very briefly, the second topic that I touched upon is that when you have neutron stars and X-ray binaries, they can be heated during accretion and then subsequently cool down in quiescence. This is something we can monitor on timescales of days to decades. Observing this cooling, especially with Chandra, allows us to study the properties of the neutron star crust and core. And this is something where the spatial resolution and soft energy sensitivity of Chandra are very important. Now, sometimes this requires very long stares because these neutron stars get very cool, they get very faint. Sometimes they might even get so cool that actually the peak of the emission is moving outside of the X-ray band more to the extreme ultraviolet. So if you want to do, you need to do long stares and you need to do them a couple of times. Now, if you do a long stare on a very cold neutron star, it can be extremely constraining. We're currently working on some neutron stars where you might actually be able to constrain the superfluid properties of the core by just staring at it for a very long time. All right, so this is where I will finish.
Thank you for that very interesting talk, Nathalie. We have about 5 seconds for questions, but we have a couple questions already. I'm going to ask one, and then we're going to have to pass the remaining ones to after the session is all the other speakers have spoken. The question is from Agniva, and they ask, assuming magnetic fields launch such winds, what constraints can you put on the disk magnetic field strength configuration using these wind observations that you have shown?
So there have been some attempts for this in black hole systems. So for example, if you look at the paper by John Miller on Giro 1655, that's where they attempt some of these things. In case of neutron stars, I'm not sure if the magnetic fields, if they play a role, if they would be the same process. It could, for example, also be that the neutron star magnetic field, because it's spinning around, is creating some kind of propeller effect. So this might be a different way of launching a magnetic wind in neutron star systems than in black holes.
Great. If our next speaker could start sharing their slides, we may come back to this question. You can also answer this question via text in a response in the Q&A, Nathalie.
Yeah, I will.
Okay, our next speaker is Teresa Panurach from Michigan State University, who will talk to us about jet accretion coupling in luminous accreting neutron stars in galactic globular clusters.
Yes, can you hear me?
Yes, I can hear you.
Perfect. I want to thank Rudy and the rest of the organizers for organizing this. I'm pretty sure you worked really hard in the middle of the pandemic, so thank you. My name is Teresa Panurach. I am a graduate student at Michigan State University, working with Jay Strader and Laura Chomik on jet accretion coupling and luminous accreting neutron stars in galactic globular clusters. Oops, let me see. There you go. So I want to thank the previous speaker, Nathalie, for really explaining why these critters are very important. So this plot we've seen multiple times in this conference, and it's the radio X-ray correlation plane for accreting compact objects. So on the x-axis, we have X-ray luminosity that we use as a proxy for accretion flow. And on the y-axis, we have radioluminosity that we use as a proxy for jets. And we use this correlation to understand the coupling that happens between the accretion disk and the jet. So I'm currently working on a systematic study of simultaneous radio and X-ray observations of 6 persistently accreting neutron star X-ray binaries and 2 other transient sources that we caught in our collaboration survey. And we want to study these critters because unlike black hole X-ray binaries, little study has been done to really understand the radio emission that comes from neutron star X-ray binaries, especially those that are persistently accreting, like my sources. And lastly, for some time now, we deduce that there is some agreeable correlation for black holes that we can see in this gray dashed line in the plot. And we want to know, is there something similar for the neutron star population? Okay, and so the data that we are using is our collaborations radio survey called Maverick, which uses the VLA, and ATCA. And so the MAVERICK survey consists of observing a sample of 50 nearby globular clusters to look for radio candidates showing signs of accretion. And for X-ray observations, we use mostly Swift and Chandra, of course. And so it was very important for us to get strictly or nearly simultaneous observations because we wanted to know what exactly is going on between the jet and the accretion disk at the same moment, since neutron stars tend to evolve super quickly. And so in our results, we show the radio and X-ray correlation plane again. And so here we have all 8 of our sources, which are the large color X's on the plot. And those with multiple X's with the same color are the same source, but we just happen to have multi observations for. And so plotting these systems, we show that neutron stars do not follow a single relation compared to the tight correlation that we see for the black holes. And we also see that after adding my critters, that neutron stars do show a broader range of radioluminosity than previously observed. And some of them can be as radio bright as black holes at the same X-ray luminosity. And thank you. I'll take any questions.
Thank you, Teresa, for an excellent lightning talk. If we have any questions, please enter them into the Q&A. I have a question. I wonder how simultaneous were you able to get with these observations?
Yeah, so some of them were taken like directly at the same time. We were lucky enough to get observations like at the exact same moment, but other times they were like at most a day or 2 apart.
Mm-hmm. And you're limiting detection in radio. Are there radio facilities that could push these limits further?
What do you mean by further? Do you mean like
so
going
that you can detect them?
Like over here?
Yeah, like you have a lot of non-detections, right, in the radio.
Yeah, I think it's because, oh, I'm sorry, my dog is barking, but a lot of neutron stars are less radio loud than black holes. So I think that's why we get a lot of like upper limits for neutron stars.
Okay. Great. Thanks so much. If the next speaker can start sharing their slides. Our next speaker is Michael Nowak from Washington University in St. Louis, and they will talk to us about Chandra eclipse timing determination of the third body period of 4U 2129 plus 47.
Okay, thanks for having me speak here. Normally, when we think of a timing mission, we think of a large effective area satellite like the Rossi X-ray Timing Explorer, or NICE, or not something a bit more small effective area like Chandra. But Chandra has a few unique aspects to it that make it interesting for timing. The first is its exquisite spatial resolution, which essentially means that it has no background to it for point source observations. So single photon events really actually can be quite interesting from the point of view of timing. And we're going to talk about that in a moment. The other interesting aspect is that Chandra's now been around for 21 years. So there's the opportunity with a lot of these sources to have very long light curves going on. And we're going to talk about that as well. So thank you, Nathalie, for doing a great introduction for quiescent neutron stars. We're going to talk about one for you 2129 plus 47. 4 years ago, this source was actually in outburst as an accretion disk corona source, which meant that it was emitting roughly at Eddington luminosity and had a broad partial eclipse, indicating that the X-ray corona in it was roughly on the size about 1/4 the binary separation. Since then, it's gone into quiescence, and that becomes interesting from the point of view of trying to understand the nuclear physics of the neutron star itself by looking at the cooling of this. Now, we can do interesting things with this because the fact that there is an eclipse in the system, as you can see on the movie on the left there, that is a Chandra movie, and there is a rapid total eclipse. Now, the interesting point is, I said, single photon statistics matter. So the light curve there on the right is from multiple observations, 2000, 2012. There's also a 2015 observation. And the phase bins you see there for the orbital phase, the error bars are just the Poisson statistics. But in the eclipse there in the middle, the small dotted line that you can see there is actually the 3 sigma upper limit to the count rate in that eclipse. That eclipse is total, and It's quite rapid and dramatic. Now, we're going to come back to this in a little bit in a couple of slides. The difference between 2000 and 2012 is that you can see that the amplitude of the light curve has dropped, and also sinusoidal modulation has gone away. We're going to come back to that in a moment. But as far as the timing is concerned, we can just look at the star, companion star, go in front of the neutron star and eclipse it totally. And the timing of the last photon that we see before eclipse and the first photon we see after eclipse, we can do Bayesian statistics on that with single photon statistics and come up with a probability distribution for the eclipse midpoint and the eclipse duration, by the fact that, again, that essentially background is completely negligible in Chandra. So doing that, and that's the upper left there, you see the probability distributions for the various different observations we've done for eclipse duration. We can get the timing of the eclipse duration to about 10 seconds. We can get the midpoint to 15 to 60 seconds, and we get a very good period to about a tenth of a second or so. But when we look at the residuals for the periods that we've measured over the roughly 15 years or so, there are strong residuals on the up to about 300 seconds. This is really indicative of the fact that what we have here is a three-body system, an inner binary orbit of about 5.5 hours, and then there's an outer F star probably there, which is going around. Best fit we have is somewhere between 200 and 500 days, and I show the probability distributions in the lower right corner, showing the different possible periods. Our favorite one right now is a 286-day orbit. Now, you do see residuals in other systems like EXO 748, which is another quiescent neutron star system that Nathalie showed, but there the residuals are on the order of about 5 seconds or so, and you can attribute that to something like a magnetic wind coming from the system. Here, because the residuals really are 300 seconds, we really need something like a third body to be going on in the system. That's potentially interesting because that might lead to the periods of outburst and quiescence due to what's called the Lidov-Kozai mechanism. Basically, you have a modulation of the inner binary orbit on timescales on the order of decades, and that might be why we see it sometimes 40 years ago in outbursts. Now we see it in quiescence. Now, the other thing that we mentioned with Chandra is the fact that it's been around for 20 years now, so we have multiple observations of this source. And the interesting thing here, as I mentioned, not only has the light curve itself dropped, but the sinusoidal modulation has disappeared. And that really is basically saying that when we first saw this, even though this looked quiescent, there really was a little bit of residual accretion going on. Now, whether that's happening for all quiescent neutron star systems is a very interesting question to understand, whether there is some amount of residual heating still happening to the neutron star surface, confusing what we think is as far as the cooling mechanisms are concerned. After that, the hardtail disappeared, the sinusoidal modulation disappeared, and there still seemed to be a little bit more cooling that happened after that. That's shown in the lower right-hand corner there. We see there's definitely cooling of the surface from 2000 to 2012. Maybe there's a little bit more cooling from 2012 to 2015. That starts getting into the issues of how well do we understand the calibration of Chandra as far as the contamination is concerned. It's a very challenging observation. That's about 90% significant there. So I will end there. Just to say, with Baramian's talk last week, the level of this source would be what he would call the difference between the disk active phase and the disk passive phase. Really much more a factor of 2 around the disk passive phase. Maybe we'll call that a passive aggressive phase. The difference between a little bit of residual accretion and not. And I'll stop there. Thanks.
Thank you, Mike. That was an excellent talk. Lots of interesting stuff there. If you have any questions, please enter them into the Q&A, and I'll have Mike answer them offline because we're out of time for questions. Will our next speaker start sharing their slides? Our next speaker is Hui Yang from George Washington University, and they will talk to us about the role of temporal features in machine learning classification of X-ray sources based on the Chandra Source Catalog. And you are presently muted, Hui. Still muted.
Can you hear me now?
Yes, excellent. Thank you.
Okay, so hi everyone. I am Hui Yang, a graduate student from the George Washington University. And today I will talk about our recent work on the machine learning classifications of X-ray sources based on Chandra Source Catalog CSC version 2 with emphasis on the temporal features. So why do we need machine learning based classifications? For one reason, most X-ray sources are discovered serendipitously with unidentified nature. For example, CSC v2 has more than 300,000 unique sources, and we haven't known the classifications for most of them. Another reason is that we have entered a time of multi-wavelengths, multi-epochs, and multi-messenger astronomy, where the data are in very high dimensionality, which makes it very difficult for humans to comprehend and analyze. That's why we need machine learning to do some work for us. The EROSET mission has conducted its first full-scale observation with more than 1 million X-ray sources found. Without the help of those methods, it's hard to keep the classification rate up with the discovering rate of those amazing telescopes. The first and the foremost part of our supervised machine learning method is the training dataset, which is a set of about 2,500 classified X-ray sources that we construct by cross-matching CSC with literature-verified sources, including 9 classes. The training dataset are very imbalanced among different classes, which can cause some bias in classifications. To alleviate this issue, we oversample the training dataset for those less populated classes of sources. We also extract information from multi-wavelength catalogs to construct 29 features that we use for the pipeline. Then we extract the unclassified data in the same way as the training dataset. At last, we feed those unclassified data to the classifier, which was trained on the training dataset with random forest algorithm. Then we can get the classifications for those sources. Our pipeline also takes into account of uncertainties via the Monte Carlo simulations. So we have 2 X-ray variability features. One is inter-observation variability, which we calculate from the reduced chi-square of multiple observations. The other is intra-observation variability, which we extract from CSC v2 directly. The bottom figure here shows the fraction of variable sources in the training dataset, and you may find that different classes have different fractions of variable sources. We use this kind of confusion matrix, which allows visualization of the performance of an algorithm. A more diagonal matrix represents a better performance. Our algorithm has reached an overall accuracy of 84%. So one of the implementation we do is to apply our algorithm to the variable sources on the galactic plane from the CSC v2, which include about 900 sources with short-term timescale variability. We have found classifications of about 400 variable sources, where most of them are YSOs and stars. Here is an X-ray flux versus hardness ratio plot for most confidence classifications in squares and training dataset in dots. Then based on those results, we will focus on those sources that we are interested in and study them in details. So I will stop my talk here and take any questions. Thank you.
Thank you, Hui, for an interesting talk showing the power of the Chandra Source Catalog. If we have any questions for Hui, please enter them into the Q&A box. I wonder if you have any, can you beat or improve the classification scheme by adding more sources? So for example, when the new source catalog gets updated for newer data.
Yes, so that's one of the way we will be doing to improve our machine learning algorithm. So, but we have to study those classified sources in details to make sure the classifications. Yeah, yeah. but we can also try to enlarge our sample of the training data set by studying some other like papers, which can provide some classifications too. Yeah.
We have a question from Manuel Arando. Does your algorithm weight source variability with the flux of the source? Bright source are more likely to be seen as variable due to higher statistics.
That's a good question. So, actually, I don't think we wait on the flux, but like we have 29 features, which include like multi-wavelength features, but some sources might not have all of the features available. So that might cause some bias if some source don't have some like observation for some wavelengths. Yeah, but we don't wait on the flux. If they all get the flux, then yeah.
Mm-hmm. Great. Okay. Thank you very much again. If we can have our next speakers share their slides. Our next speaker is Nanda Rea from the Institute of Space Sciences.
Hello, everyone. I'm sharing the slides. If I can.
And Nanda will talk to us about strongly magnetized neutron stars in the Chandra era.
Yes. Okay. So, hello, everyone. Thanks for the preview, for the invitation to give this talk, and to the previous speaker for the fantastic talks too. So what I will speak now, so I will somehow change the subject a bit, but will be the subject of the next section, part of the next section, are about isolated neutron stars. And in particular, I will show you the great contribution that Chandra gave to the study of strongly magnetized neutron stars. Before entering, speaking about strongly magnetized neutron star, let me somehow make you a bit familiar with the different pulsar classes that we actually know in our famous PP dot diagrams. There are plenty of them. So there are mainly the difference. It's so far has been divided by the kind of emission they were showing. That could be thermal emission, like case of X-ray dim isolated neutron star. They were magnetic emission for magnetars, or rotational powered for pulsars. So somehow those classes were divided as such, depending on the observational properties of these sources, and hence on the kind of emissions that we thought actually could be in place in the emission of this kind of object. Let me start a bit with the magnetars to somehow introduce them to you. So before Chandra and XMM, I would say, so before the new generation X-ray telescopes that we have now, very little was known for these sources. So there were more or less 10 sources before the Chandra launch. And of them, the main idea was that the X-ray emission that they were showing, they were either steady or bursts. This X-ray emission was too bright compared to their rotational energy. So at variance with the normal pulsar that were well known at that time, this emission should have come from a different kind of energy budget. And this energy budget, because of the P and the P dot of those sources, were soon thought to be the magnetic energy, because the magnetic dipolar field that we could calculate from the P and the P dot was of the order of 10 to the 13 till 10 to the 15 Gausses, depending on the sources. Now, at that time, people started to work on this kind of object from a theoretical and also observational point of view. And the idea is that you could have somehow a critical magnetic field below, which is 4 10 to the 13 Gauss, below which you could have pulsars and above which you could have magnetars. And this critical field was sort of a theoretical limit that it's somehow the magnetic fields for which the cyclotron energy of an electron rotating around it, it's equal to its rest mass. However, Chandra came, XMM came, the new generation telescope came, and things changed enormously. This is where we are now. Thanks to these telescopes, we know plenty of these sources. We understood that many of the things that we thought before were actually not correct. They are mostly powered by magnetic energy, but there are some of them which have strong also rotational energy. They are very variable. They have actually magnetic fields. They might have dipolar fields, which are lower than the critical limit. So things got very complicated. I will show you now, I will go in details in some of these new results because they are extremely interesting also then to understand somehow the reach of the Magnetary activity of the high magnetic fields in the whole neutron star, isolated neutron star population in our galaxy. Let me just introduce you a bit observationally what those Magnetary bursts are. Those are things of this kind. Those are all X-ray observations. They can be short bursts, the one you see on top, or what we call intermediate flares. They are a bit longer, a bit more energetic, or what are the giant flares, which are a bit more rare, but very, very powerful, probably actually second only to supernova explosions in our galaxy in luminosity. Now, connected somehow to this kind of bursts, which are very short, so usually, I mean, they are interpreted to be coming from the magnetosphere of the sources of this very magnetic neutron star. They are connected also to some persistent X-ray emission changes, which we call outbursts, that can last months or years, even decades, even 1 decade sometime, and they have different cooling. So what happened in that? What happened is that you have this very complicated magnetosphere for these sources. The higher parts of the magnetosphere can break and reconnect, can cause you your short bursts, which are very energetic and very short. But this is somehow connected to change in the magnetic field and twisted either locally or the whole magnetosphere close to the surface. This means that when this twisting happens, the whole surface gets very hot and the outbursts occur. And then the surface cools down. Of course, this, depending on the region you hit, the outbursts can be bigger, can be smaller, can be longer, can be different kind. But it somehow relates to energy injected in the crust and then re-emitted and cooled down. Those are some models, some preliminary model we started to do several years ago. Things we understood in the meantime, then things are way more complicated at how we were modeling them. But somehow you see that depending on the kind of energy, you see this is luminosity as a function of time, depending on the volume in the neutron star that we simulate and the energy we put in this volume, then the light curve can behave differently. And many of the outbursts, as you see on the right, that we see from these sources actually can be easily modeled in this way. Now, some important object for which actually we understood that this was not the whole story. This is the case of the Galactic Center Magnetary, for example, for which Chandra gave a fantastic data set, probably unique in the Magnetar outburst study, on the evolution of the outbursts of this source. This source is very interesting, apart from being a magnetar, also because it's probably the closest neutron star to a black hole ever observed, and at least in radiation, because in gravitational waves, we don't know. So this is a magnetar which is extremely close to our supermassive black hole, as close as 0.1 parsec, more or less, and went in outburst in 2013. Chandra was the only satellite at that time, actually even now, the only satellite that had the spatial resolution to distinguish the X-ray emission from Sagittarius A star and this magnet. We monitored this for several years, and you see on top, those are all Chandra data that only the resolution, spatial resolution with Chandra could actually give us this long-term monitoring. So you see this fantastic spectrum, and on the right, you see the modeling of them. So this source is a perfect black body cooling down. So in this sense, the model, the general model of those outbursts were correct, the one I was speaking about. But one thing that we understood, thanks to the extremely detailed data that we could have, that this is not the whole story, because the cooling of this source, it's definitely too slow for whatever cooling model that we can apply. So it's not, so this can be due to several things. Either currently, we don't know so much about the physics of the neutrino emissivity, for example, under strong regime, that can be less efficient than what we think. And this is why we have the source brighter than what we think, than what we thought in the modeling. Or there is a strong magnetospheric also heating. This is for sure there is, but there is a long-term magnetospheric heating in a bundle that gives most of the energy rather than coming only from somehow inside the crust. So this is one case. Actually, another case we just studied of this exception of our cooling models for magnetar outburst is this other magnetar, which is very famous, 1547, for which again we found, thanks to Chandra, XMM, NuSTAR, and many other many X-ray telescope, that the source it's too bright than what we could expect after an outburst in the cooling, than what we can anyhow model with any kind of cooling models. So this it's one of the new things that was understood thanks to all this detailed data, that there are other effects that should be taken in account to study the cooling of these outbursts, that at the beginning were thought to be somehow a holy grail to then infer some information about the crust of the neutron star of these magnetars. But actually things are not that easy. So we have to go deeper to then somehow get studying into the crustal composition. Other interesting sources for which Chandra gave fantastic data and great results in the past decade or so are the low-field magnetars. Those magnetars are sources that at the first glance, they are exactly like the other magnetars. So they show typical bursts, typical outbursts, very bright X-ray, their spin, their P dot. The only difference is that when from the spin and the P dot, you measure the magnetic field is extremely low, at least the dipolar one. So it's so low that in principle, their X-ray emission is not justified. It's too bright for if this is the only magnetic field that they actually have. This opened the understanding that there is not only the dipolar field, which is crucial for all neutron stars actually, but there are other components of the field which are very important. And a work in that direction, for example, in exactly for one of these low field magnetars is the detection of a possible line with a shifting in energy that could be due to actually a loop close to the surface, which has a magnetic field, which is 10 to the 14 instead of 10 to the 12, that it's the dipole that we measure. And this can somehow cause the strong X-ray emission and strong outburst, which might not be reflected by the dipolar field that we measure. Other classes like thermal neutron star, I will only show these results because this will connect to the end of my talk. Very recently from these sources, similar spectral lines that the one that I've showed for the low field magnetar has been detected. This is very important because this somehow pushes the idea that those objects are actually old magnetars that had decayed, it's just very old ones, and that still have these loops of strong magnetic field close to the crust, as very young magnetars do have. Changing class, let me pass to central compact objects. Those are mainly thermally emitting sources at the center of supernova remnants, very well observed by Chandra, because you really need very high spatial resolution to resolve them within the very bright remnants. A very famous one is Casey, for example, but there are several others. For some of them, a spin period and a P dot could be measured. And as you see in the PP dot diagram, they have those for a measured PP dot, they have a very low magnetic PP dot and very low magnetic field of the order of 10 to the 10, 10 to the 11 Gauss. This was this detection of the period and period derivative and magnetic field was very shocking at the beginning because they are very young. We know they are young because they are the center of supernova remnant, but they have very low magnetic field. So either something made their magnetic field very low, or somehow this might be a demonstration that there are two peak in the magnetic field at birth of neutron star, one very low and one very high for the normal pulsars. Now, studying this more indeed, we've found a few years ago in one of those sources a very strong outburst related, very similar to the one of the Magnetars. This source, it's RCW 103. It's a very famous remnant. You see on the left the swift of the images of the source while the central source was in quiescence and when it was in outburst. And on the right, the beautiful image that Chandra could do of the remnant of the source during the outburst of these central compact objects. Now, the interest in this is that it showed an outburst has a magnetar, so this means that somewhere it should have a strong magnetic field, because there is nothing that we know about for an isolated neutron star that can cause this kind of bright outburst apart from a strong magnetic field. Now, but another interesting point is that this source has a 6.4-hour periodicity in their light curve. And you see the light curve here below, both from the Chandra and XMM data. Now, 6.4 hours, it's very slow for an isolated pulsar. So the main point is somehow closed the question on how this period, this long period and the magnetar activity could have been produced if the supernova explosion in this case, which happened about 2 kiloyears ago, had a very strong fallback accretion. So with a very strong fallback accretion, if this was formed as a magnetar, this strong fallback accretion could have slowed down a lot the source, which could be even now in a very long, somehow at the end of a very long propeller regime somehow, and in 2 kiloyears could have slowed down something that was born at 10 to the 14 Gauss with a few milliseconds to a 6-hour spin period. And this might happen also to other CCOs that could indeed be sources with a lot of fallback accretion for which their strong magnetic field is now mainly inside the crust. So this is the dipolar field that we see outside is actually what left of the dipolar field, but close to the crust, they have very strong magnetic fields. Other sources which actually showed, again, magnetar-like activity somehow are so far a couple of rotational powered pulsars, which are those two very famous Chandra targets because they have extremely bright and interesting super pulsar wind nebulae. So you see on the right the case of PSR 1846 with its parts wind nebulae. Those are two Chandra images, and you see when it was in quiescence and when it got in outburst. Those objects, especially PSR 1119, are certainly rotational powered because in this case, for example, they are radio pulsars, normal radio pulsars that at certain point decide to emit a large amount of magnetic energy in an outburst, similar as a magnetar. This opens a lot of questions. So I somehow showed you the new results, the last results in the last decades, where thanks to Chandra, thanks to XMM, we could understand how magnetar emission, bursts and flares connected with magnetar-like structure are present in almost all isolated neutron star classes. This opened, of course, several questions, first on formation of those magnetic fields and on the birth property of those sources. So, which is how they are born and how do they evolve to somehow at a certain age behave either as a thermal X-DINs or as a CCO or as a very bright magnetar. So this helped to start to model with an evolutionist scenario the different classes, especially because if we consider them as isolated classes, we run out of supernova explosions in our galaxy. So they should somehow, at certain point, a magnetar become a X-DINs, or a rotational powered pulsar might become a very faint X-DINs in order to have enough supernova explosion to form all these different classes of neutron stars. And it's also clear that a big role in this is actually the magnetic field strength and especially the geometry. So where those loops are actually formed in the crust, how do they evolve and how strong they are. This it's somehow in line with recent simulations of magnetic field formations. Those are recent simulations which for the moment can only last very less than a second, and are simulation of a proto-neutron star, so still everything is liquid because they are extremely complicated from a computational point of view. But it's already clear, as you can see in this video, is already clear that the magnetic field, when you form it in a proto-neutron star, is very chaotic, and it's actually easier to form small, very strong magnetic field loops than a very ordered dipolar magnetic field. And this is something we understood thanks to all these observational results and subsequent theoretical work just only in the last 10 years or so. Sorry. So from the evolutionary scenario that we are trying to use to model all these classes is based on evolving the magnetic field. So those are two plots where you can see on the left thermal luminosity in the X-rays and age. And on the right, where age, it's either the remnant or from proper motion, or you see an arrow if it's characteristic age. On the right, you see the same sources in the PP dot diagram. So it's somehow what it's shown here that depending on the initial magnetic field and the initial topology, the evolution that you expect for such sources are different and are extremely connected in the luminosity diagram and in the PP dot. In particular, some simulations on this magnetothermal evolutionary model shows, I can tell you details if you have question later, but shows as a function of the magnetic field, where you see the very low one on top right and the highest one on bottom left, you can see the evolution in time, and you can somehow reconstruct the age, the progenitors, and also what will be the future of almost all the sources in the PP dot diagram, just changing the magnetic field configuration and at birth and making things evolve. Configuration, geometry, and strength especially, and make things evolve. Now, to summarize, to the last part of the talk, I will show a couple of recent work that we did to try somehow to compare and study how this Magnetar population, how can we use them to somehow help the interpretation of many of the transient events that we know in our galaxy. Then many of them recently have been interpreted somehow in connection with the Magnetar population, both in long gamma ray burst, even in short gamma ray burst, because some of them actually do show a plateau in their emission, in their afterglow emission, that might be due to a temporary magnetar that is formed, temporary or long-term in some very small percentage of cases, and also fast radio bursts that you will see in a talk in the next session, are also somehow connected with the emission of magnetar bursts and with the existence of magnetars. So a recent work that we did in my group, and this is a work by a PhD student of mine and Daniele Vigano, which is Clara Deman. So one of the things that we can do with the magnetothermal model that has been built for the evolution of magnetars is to study somehow at which and how often and how early after the formation of a magnetar, actually one can expect some crustal failures of the crust in the magnetic history of the source that might be the driver somehow of burst and flare, and then also of fast radio burst. This is somehow to try to connect the rates of magnetar burst in early young magnetar to possibly the rates of fast radio burst, so of possible young magnetars in other galaxies. So one thing that has been understood by this work, I think it's for me it was very, very, I was astonished because I didn't expect that, and I think none of the quoter possibly did at that level, that the main point is not actually the dipolar field that those source has. Sorry, this E deep should be B, should be the magnetic field. So those two simulations, for example, showed two different configuration of the field, the one that I put in gray, where you have certain B dipolar, certain magnetic energy within the crust, and you see when you expect the first event and some other parameters, and which is the rate of events you expect in 1 kilo year. And you see that with the same dipolar field, actually, there are a huge difference in when you expect the first event. Actually, in the first case, you don't expect to have any in a kilo year. And the reason for that we understood, this is another example of other configuration, other kind of configuration, for which in one case, there is also a component in the core of the magnetic field. So there are different configurations that we have studied. And the main thing that we understood that at the same dipolar magnetic field, actually the rate of the crustal failures can be extremely different. And also when we expect the first after formation can be very different. And the main driver of it is actually the magnetic energy in this crust and not the dipolar field that you have.
2 minutes.
Yes, thank you. Last work that I would like to show, also related somehow to the connection between Magnetary bursts and fast radio bursts that we will hear in the next section, so I will not go deeper in that. It's a result that was a paper that it's now in submission, that was somehow, there was some results showed in a proceeding several years ago by Marta Burguet. So finally the paper is finished, so I can show somehow more detailed results of it. So this is some FRB-like, because they are fainter, they are dimmer than FRB, radio burst that has been detected from 1547, which is another magnetar, during an outburst of in 2009. So we had those two sets of observation with Chandra and Parkes and with XMM and Parkes. And you can see here the XMM light curve, and very soon after, only less than a second after one of those bursts, which is burst 2, that was also observed by Swiftbat and by Conus Wind, actually we detected with Parkes 2 subsequent bursts, the first of which actually saturated the detector, so we don't have a real determination of the luminosity, but we know that was larger than a Jansky for sure. And it was more or less 1 second, only slightly less than a second after the X-ray burst. So this is somehow another point of the puzzle that points somehow toward the fact that there might be a continuum of radio bursting during magnetar bursting emission. The brightest one was the one so far, the one from 1935, that actually also showed other radio bursts fainter than the one which had the X-ray counterpart. And also this is another source that showed a similar thing, fainter than the first one detected, but still possibly connected with the X-ray burst, although not strictly simultaneous. This probably, I guess, is showing that there are several factors. There are several X-ray bursts without a radio counterpart. There are several radio bursts without an X-ray counterpart, and also simultaneous and not exactly simultaneous bursts. So there might be a geometry effect in the connection between the two, and more detection of this kind probably will slowly show us the complete picture of this, and also the connection, hopefully, with the extragalactic fast radio burst. Thank you very much.
Thank you, Nanda, for excellent talk. We have a couple of questions.
Yep.
One question is from Tugba Bozet. Thank you for your informative speech. I am so sorry that I missed that part. Could you tell me again how we can understand Magnetar from other neutron stars? Is it the same valid is the same assumption valid for timing analysis?
Okay, so the first part is, so when one thing that is getting clear from studying proto-neutron star simulations of supernova explosion is that there are several MRI instability, several things, convection that can happen in a neutron star when it's still liquid that can easily form loops of 10 to the 15 Gauss. So there is absolutely nothing against, and actually it's highly probable that those strong field small loops components are ubiquitous in the neutron star population. Of course, sources that might have more, sources might have less. This depends on how, probably on how they were formed, on the massive star progenitor, on how the explosion happened, on many other things. So this is probably the reason for which we see magnetar emissions or bursts and flares in object, and when you then measure the dipolar field has only a 10 to the 12 Gauss, or from radio pulsar like 1119, which are radio pulsar, but at certain point it shows magnetar-like activity. Because apart from the dipole, there is a huge amount of magnetic energy stored in other components of the field that are not on the dipole, that aren't necessarily close to the crust, can be stronger or dimmer in other pulsars, but they should be there because that pure dipole in nature actually cannot be formed. There is no way to form a pure dipole. I don't know if this, from the timing point of view, this is not a problem because the timing analysis only sees the dipole because it's the larger structure. So the small structure close to the crust do not affect much the timing, but do affect the temperature of the surface, the luminosity, and possibly their bursting activity if they should burst.
Great. We have a question from Mark Elowitz. Can the process of magnetic reconnection occur in magnetic field environment, thus leading to the acceleration of charged particles in the magnetar environment?
Sorry, say it again.
If you look in the chat, it's there.
I'm trying to, that I don't see my mouse in there
so
while sharing.
The question is,
I don't see it. Yes.
Can the process of magnetic reconnection occur in the magnetic field environment, thus leading to the acceleration of charged particles in the magnetar environment?
Yes, absolutely. Can well happen. And actually many of the bursts, the short bursts and the flares, probably this is, it's due to magnetic reconnection higher up in the magnetosphere, yes.
And we have a question from Pat Slane. Isn't there a disconnect between the number of magnetar supernova and the inferred rate for formation of magnetar neutron stars?
So the point is that I'm not sure we can really define what a magnetar supernova is, in the sense that in a normal supernova, things, small structure of 10 to the 15 can be easily formed by MRI. So you can form a 10 to the 13 pulsar, then evolves like a normal pulsar, but it has, when it's young, for example, a very strong loop that at certain point create the bursts. So it's very difficult to, and this is not a strange supernova that might have formed it. So I'm not sure if I understood the question, but I don't think we can actually claim a magnetar supernova and a normal supernova. There might be some drastic thing in the sense that sources like SGR 1820, which we know have a very strong twist, very strong magnetic field, and being very young, it might be that the supernova that had formed this should be possibly a highly magnetic star to start with, very rotating one with a lot of convection, or binary too. So the more convection we have in the proto-neutron star, the more magnetic field or tangled magnetic field we can form. But I'm not sure we can really distinguish so easily, and hence compare the rates directly.
Mm-hmm. If you have any questions for Nanda, please enter them into the Q&A. I had a clarifying question. So the simulations you showed us, where you showed us that the magnetic field structures on the surface were really chaotic. That doesn't have to do with the global bipolar field. That's just real close to on the crust, or is that?
Well, in this simulation there is no magnetosphere.
Okay.
So So yes, this is for the moment. There are other simulations that has been done that do consider not, let's say, without considering all the physical effects in the crust that this simulation consider, but looking at more at the magnetosphere. There are some, but
where you'll get that that ordered dipole and this chaotic structure, or
yes.
Okay.
Yeah.
Great. If there's any more questions, we have about time for one quick one. We can also open up the questions to everyone on the panel if you had any additional questions for any of the speakers in this session. If not, great. Then I'd like to thank all the speakers again for an excellent session. And I'd like to remind you that our next session, is starting in about 30 minutes. And remember, it's a different link. That session is going to be on a continuation of the neutron stars and magnetars topics. Thanks again for joining us, and I hope to see you at the next session.
Thank you.
Bye.